Good afternoon, everyone. Welcome to another edition of the Tech Exchange Seminar Series. This is for the Spring 2026 semester, and we have a late start. The objective of this series is to try to get people working in different areas in AI and adjacent topics to promote their work across the university and try to see if we can build some collaborations. And so in that in our series this semester, so we have in our starting session 2 talks, one from Professor Anne Talkington from the Department of Pharmaceutical Sciences, and I will hand over the mic to her to present her work.
Thank you so much. Is everyone able to hear me? Is this... Ooh. Okay, we're okay? All right, so I'm really excited to be able to share some of my work today, hopefully spark some new collaborations. I'm a new-ish faculty with IAD. I just joined UB last year in the Department of Pharmaceutical Sciences, and very briefly, my work focuses on computational drug optimization. The project I'll talk about today is applications of that and how we can quantify immune activity, perturb immune activity through therapeutic interaction, and use these sorts of methods to optimize treatment strategies in a solid tumor microenvironment. All right, so starting off with some statistics, I don't really think I need to give too much motivation on how much of a serious public health issue cancer still is. However, I will start us off with a few statistics. Notably, I've listed a few types of cancer here, arranged in descending order by deaths per year, estimated deaths per year in the United States. And what I would really like to point out is some of these disparities. While some cancers are still considered relatively treatable, for example, melanoma, this ratio of deaths to new cases per year is less than 0.1, which is it's still something, but much better than we're doing in a lot of different cancer types. However, if you look at the rows highlighted in red, including lung cancer, pancreatic cancer, and liver cancer, that far right column, the deaths to new cases diagnosed ratio per year, is much, much higher, as high as almost 0.8 in pancreatic cancer, which really indicates that we have a long way to go as a field in terms of understanding why is standard of care not working and how can we potentially improve upon standard of care strategies. So I think about these types of problems as sort of a two-pronged approach. So we want to think about addressing questions of drug delivery. So are we getting a drug to its target site? And then drug activity. So once the drug is at the target site, is it doing what it needs to do? For purposes of today's talk, I'll mostly focus on the smaller scale drug activity question. So is our drug behaving as we want it to once we get it to the solid tumor? And one way that cancer cells are really able to notoriously escape treatment, one of the reasons they can be so difficult, is through this mechanism of cellular communication via inhibitory receptors. And this is a mechanism that we are attempting to treat. So by way of a little bit of background, cancer cells are very, very good at selectively turning the immune cells off. So if we look at this representative immune cell, it's covered in a set of what we can think of as off switches or on switches, so stimulatory and inhibitory receptors. The T cell here has a lot of off switches and a lot of on switches, but this antigen presenting cell or tumor cell is really, really good at selectively binding to the off switches. In a normal, healthy environment, there would be a balance of these signals so that our immune system is able to respond to an infection, but then downregulate before we reach a state of hyperactivity or autoimmunity. Cancer is really good at just turning it off, keeping it turned off. And one of the ways that we try to prevent that is through immune checkpoint blockade. So we can think of it like putting little caps on top of the off switches. So when our antigen presenting cell or our cancer cell interacts with a T cell, we've sort of shifted that balance. So instead of selectively binding to the off switches, there aren't as many off switches left to bind to. So now we just bind to the on switches, at least in theory, turning the T cell on, keeping it in an active state. This is an example illustrated for CTLA4 or an anti-CTLA4 antibody, which is one of the on-the-market immune checkpoint blockades. However, again, if you recall from some of those initial statistics, we still have a long way to go as a field in terms of making these strategies as effective as they possibly can be. So I like to think of how can we treat this as an optimization problem? How can we optimize this immune checkpoint blockade? And more specifically, can we design a blueprint for what that ideal checkpoint blockade would need to look like? So there are a lot of ways we can think of optimizing an antibody and what it would need to do. So one of my initial questions was looking at, is there a critical threshold of the number of off switches or the percentage of off switches we need to cover to try to keep our cells in a sufficiently active state? This first part of the talk is largely work that was completed in the past year in my position as a National Research Council Fellow at the National Institute for Standards and Technology. So setting up the groundwork for the work that my group is doing now at UB. And very briefly, I won't talk through the equations ad nauseum, but essentially we adapted some sets of ordinary differential equations to try to capture tumor immune interaction dynamics and notably introduced, this, this coefficient A, the rate of cellular exhaustion. So accounting for this phenomenon of cancer cells, T cells interacting. And then this parameter I, the immunotherapy parameter, accounting for how much are we allowing this process or not allowing this process to happen. Sweeping through our parameters, we've noticed that pretty consistently at values of I, so this immune checkpoint blockade, corresponding with 80 to 90% cell surface coverage, it's when we started to see this sort of binary outcome essentially become a 50-50 split. So the options, if we consider our cancer cell, T cell population phase plane, looking at the proportion of cells or cell fates in the tumor microenvironment, our simulated patients tend to achieve either a high cancer, low immune steady state or a high immune, low cancer steady state, which is the one that we want. Again, once we get between 80 to 90% blockade, that's where we start to see the shift from being more cancer cell dominant to more immune cell dominant. So now that we've sort of defined that threshold, we've went and added some noise to this dynamical system, sampled through larger distributions of all of our parameters, saw what looks like a little bit of a hairball now in our phase plane because we can have now tumors of different sizes, for example, or some virtual patients would take more or less time to eventually reach their steady state. However, that doesn't change the fact that the 80 to 90% immune checkpoint blockade was holding pretty consistent as where this 50-50 cancer, no cancer split seems to happen. We also noted that there's a relationship between our cell birth and death rates, or specifically our immune cell birth and death rates in our tumor microenvironment, and the immune checkpoint blockade, essentially indicating that there is some critical threshold of immune activity that would be necessary in order for this checkpoint blockade to remain effective, which does really kind of make sense if you think about it. If you have what we would call a cold tumor, so not that many immune cells, we would need to really, really make sure that those cells are active so they can work a lot harder to try to keep the cancer in check. Versus if we have what we would call a hot tumor, so if there's a lot of immune cells, then we don't necessarily need to be as careful, or the therapy maybe doesn't need to be quite as particular just because you have more immune cells that could handle the job. All right, so kind of shifting gears a bit, now that we've talked about some whole tumor immune dynamics at the whole tumor level, we're going to zoom in a little bit more to an agent-based model discussing what are some of these behaviors now at the individual cell level. So we talked kind of theoretically about what does the average T cell need to look like, how covered do its off switches need to be. But then how do those dynamics sort of play out when we zoom in? Like, what does each individual immune cell in the tumor microenvironment, like how is it affected by its neighboring cells and its local, I guess what we would say is its local neighborhood. So what sort of limitations, like oxygen or nutrients, is it feeling? What other cells is it surrounded by? So we've begun to develop an agent-based model to sort of address these questions, tracking our immune cells through time and space. This is a very, very early prototype of this agent-based model in which our blue cells represent our T cells infiltrating our magenta, which is the block of cancer cells. And what we've seen from some very preliminary analysis, which was recently published just a few months ago, is that we start to see some of these patterns or regions developing of immune activity. I don't want to read too much into these data just yet because there was a lot of randomization that went into initializing this particular simulation. However, I'm very excited because if we look at cross-sections of a solid tumor from medical journals from histology, we do start to see little pockets of immune cells forming within the solid tumor, making me very curious about any sort of pattern formation that might be occurring, and that we do sort of start to see from our initial agent-based model. So to orient you guys a little bit, if we look at these, the top plots, going down means we're progressing through time. Each column represents a T cell, and blue or more blue represents less exhausted. Magenta represents becoming more exhausted. So very, very briefly, what we see is these little pockets of magenta. Those are the more exhausted cells versus our simulated blockade example on the right, which is the same simulation except imposing, again, a simulated blockade as we would expect. These plots are a lot more blue. And then when we pick out individual T cells and look at their exhaustion trajectories over time, we see that, well, trajectory-wise, like shape-wise, they look pretty similar. But this y-axis on the left, the no blockade, is much higher than the y-axis on the right, the high blockade type of simulation. So this really lays the groundwork for some of our future and really ongoing questions about how can we simulate treatment, what other variables can we consider about simulating treatments in the solid tumor microenvironment. One bit of a side note, if anybody has experience with immersive visualization, this is a bit of a side project that I worked on during my time at NIST. We had a cave system, a cave virtual reality environment in which we were able to project our tumor and immune cells really in a room with us, walk through the solid tumor, and start to see these pockets of immune activity forming in real time. And it was so valuable for being able to see, for example, if we have one random exhausted T cell and we want to see why, like who is it interacting with? Like what cancer cells is it getting stuck between? Like why would this behavior look the way it does? It was amazing to be able to really zoom in and out of the solid tumor and track those individual cells in the center of the tumor, looking through time and space. So very excited about the potential of hopefully continuing some of this virtual reality research. All right, so back to our tumor immune activity over time question. So specifically the story of how can we understand tumor immune activity in space and time and then intervene through different types of treatment, ideally optimized treatment, and try to keep our immune system as active, as primed as possible to be able to respond to that tumor. So I'll revisit some of these dynamics I've sort of introduced previously. The idea of the next iteration, I'll say version 2 of this model, is now are we not only accounting for these dynamics, the antigen presenting cell interacting with the T cell in an attempt to turn it off, we're now introducing therapeutic antibodies. So in version 1 of the model, we were inducing I'll call it a blanket blockade. So essentially saying, or just making assumptions that the blockade is uniformly distributed in the tumor. Each T cell has more or less the same probability of becoming exhausted given an interaction. Each T cell has more or less the same probability of becoming exhausted given an interaction with a cancer cell. Now we introduce these therapeutic antibodies that can bind or unbind to these off switches. We're now simulating these dynamics explicitly. The antibodies can bind to the T cell. They can even go for a ride on the T cell and then become unbound somewhere else in the tumor. So now we're not only accounting for cells moving around, we're accounting for antibodies diffusing into the tumor and then potentially moving around the tumor. Now, this is where things start to get a little bit juicy computationally. My postdoc, Jordana, has done an amazing job of advancing this model, adding more and more new features to this model. And where we're at now is essentially an agent-based partial differential equation hybrid model in which we have a combination of on-lattice and off-lattice activities. So our cells or our agents are moving around again through time and space in this simulated tumor off-lattice. We've defined a lattice to be able to solve our PDE as we diffuse our drugs into this solid tumor. And then some of the dynamics we're accounting for, essentially the agent-based model is considering both intermolecular forces and chemical signaling as ways to determine how are the cells moving around physically. The chemokine signaling is particularly important because it's what draws the T cells to the tumor initially in the first place. So we're sort of getting that infiltration. I like to think of it as the T cells it's like a sort of homing mechanism. The T cells start to burrow into the tumor. I have a video coming up very soon. It looks very cool. The PDE model, again, we're treating it sort of as a diffusive agent. We have our monoclonal antibody therapeutics binding and unbinding from these receptors as like a blockade. And then essentially what this model allows us to track is the number of interactions and what we're predicting as the exhausting interactions between T cells and cancer cells. So looking at immune exhaustion potential. Also tracking a little bit more specifically how many antibodies are bound to any given T cell at any given time. And also some other just behavioral features of the T cells, like where are they going? How fast are they moving? So here is that video. We see a set of T cells. We're assuming that a blood vessel was initiated on this outside of the tumor. The T cells are burrowing into this layer, this core of our solid tumor. And over time, I'll direct you to these still frames. Our heat map is tracking the number of potential exhausting interactions in this system. So we see the cells as they encounter more cancer cells, they get deeper and deeper into the tumor. They start to become closer to this red, this top of the color bar, indicating that even as early as after the first hour of simulation, these cells are really starting to trend towards exhaustion, which is, believe it or not, that sounds like it could be pretty fast, but it does actually track with some published literature suggesting that cells, upon initial encounter of a cancer cell, a T cell can become exhausted as early as 6 hours. So we're really starting to capture some of those early phase phenotypic changes in the T cell, looking at these tumor immune dynamics. And again, to really draw your attention to this one primary output of interest, the number of potential exhausting interactions, that's essentially just an inverse relationship between, or an inverse relationship to the surface receptor coverage. So more or a higher number of antibodies bound to a cell surface means that that cell is less likely to become exhausted and vice versa. So this is a slightly different visualization of our same simulation. Here we're explicitly showing the diffusion of our monoclonal antibodies. So the previous simulation was just looking at the tumor immune dynamics. This simulation, this visualization, we have our red diffusion cloud representing therapeutic antibody diffusing out of a blood vessel. Again, our sphere is our solid tumor. Our T cells are sort of milling about towards the core of our solid tumor. And one question that we're really asking, coming to essentially our primary central question that we've been trying to answer, which is, how else can we optimize these antibodies? So we've talked a lot about receptor coverage, what we think might be a decent average threshold for receptor coverage, but what else can we optimize about these antibodies, and what properties of the antibodies themselves would make it easier or harder to achieve that ideal coverage on an individual cell basis? And one of the parameters we keep coming back to is this binding affinity parameter. So the ratio of binding and unbinding. And what we see, so the ratio of K on to K off would be KD, our binding affinity. And what we see is that if we look at our mean number of calculated exhausting interactions, which again, as I've stated, is sort of the inverse of mean receptor coverage as we've calculated it, we start to see that higher affinity antibodies tend to result in a relatively widespread, but I'll say higher receptor coverage and lower exhausting interactions on average. However, that's not necessarily the full story. So drawing your attention to these far right plots, where we're visualizing on average the fastest and slowest T cells in the system, and then it's compared to an average T cell in the system. We notice that in these lower, so this top plot would be the lower binding affinity. We see even our slowest T cells, maybe they start to become exhausted relatively quickly, but the slope is relatively low, so indicating potentially a more sustained effect, like a weaker but more sustained effect. However, these higher KD or higher binding affinity antibodies, they seem to work really, really well for about, looking at some of these slowest T cells, they work really well for about 2 hours and then drop off. So what we suspect is happening is that there's a process of, or I'll say even some sort of region dependent effects in the tumor. So this is maybe when an antibody binds, or a lot of therapeutic antibodies bind to a T cell. They'll stay bound for maybe those 2 hours. They'll unbind. Maybe by that point, the T cell has migrated to a region where the antibodies, if they haven't necessarily diffused that far into the tumor, it has no new antibodies to pick up. So then it's stuck and it becomes exhausted. Whereas in a region of abundant antibodies, our hypothesis is that continuous binding and unbinding processes might potentially be able to sustain the T cells in a slightly more active state for a little bit longer. Again, this is ongoing work, and we're in the process of doing a lot of sensitivity analyses, but these are sort of the dynamics. We're looking at rapid effects versus sustained effects, and then region dependence, looking at where is the T cell in the solid tumor, and how well have the antibodies penetrated or permeated that solid tumor. So just to sort of wrap things up quickly, I'll just introduce the idea that my graduate student, Tlu, has been working very hard on, which is taking all of this a step further to really define, again, at this individual cell level, what do some of these trajectories look like? If we think about a cell in time and space, we've shown that it is becoming exhausted with some probability, dependent on the number of receptors that are bound to it. But then what do those activation and exhaustion curves look like? They could be influenced by a number of factors. Again, how many interactions does a cell have with other cells in the environment? How many antibodies is it bound to? There can be a lot of intrinsic randomness and stochasticity for whether or not cells interact. How robust is the T cell itself? Maybe it's more or less resistant to some of these exhausting effects versus others. Maybe that particular cell just has a really low surface concentration of something like PD-1 or CTLA-4, so it's not as receptive to some of these exhausting signals, for example. So there's a lot of randomness that could be going on a cell-to-cell basis. Here's a very similar model to what I've previously shown that Tlu has been working at tracking. What I'll really point out is whereas Jordana was tracking primarily exhausting interactions or potential exhausting interactions, Tlu has defined an exhaustion level for each of her T cells. So each individual T cell in this system, she's also defined as indicated by the circle, what she calls the hypoxic core of this tumor. So we're also looking at additional environmental limitations that these cells might be facing. Again, we can sort of see in this simulation, the little gray dots are drugs starting to diffuse in the system. We see over time cells becoming progressively more exhausted as we're sort of taking a slice, stepping through this tumor. Particularly the cells in the hypoxic core are leaning towards this sort of maroon color, like the very, very exhausted ones. And when we take all of the cells and plot their exhaustion activation trajectories over time, this is essentially what we're seeing with, again, a little bit of randomness. Pretty quickly, the cells start to become activated. Then over time, the activation sort of peaks and falls off, whereas the cells start to enter what we would call a terminal exhaustion phenotype, where they're just sort of useless in that tumor. They're just taking up space. So we're actively working on conducting some experiments in the lab to parameterize these curves according to actual markers expressed on the cell surface. So wrapping things up, so far we have defined a number of ways that we can consider optimal immunotherapy. What does optimizing a treatment mean? We've addressed this question through a dynamical systems approach, an agent-based model approach, a PDE approach, done some sensitivity to look at the robustness of T cell dependence on cell count, the properties of the antibody itself, as well as that receptor coverage. We've tested this again at the whole tumor level through a dynamical system and at the individual immune cell level through our combinations of ADMs, PDEs, and then our immune cell exhaustion trajectories as we've defined them. Through the system, essentially our goal is to be able to track simulated immune cell fate in the tumor microenvironment and then work to design treatments to keep these immune cells in as active a state as possible in giving them their best chance to be able to attack this tumor. So overall, the goals of our lab essentially involve taking a modeling and simulation-based approach integrated with some biological experiments to work towards optimizing translational immune therapies, keeping our immune system in as healthy and regulated a state as possible. Very actively looking for collaborations. If any of this sounds exciting, I've provided my email here. In particular, a lot of our agent-based models and PDEs are very numerically complex. A lot of our optimization programs are very numerically complex. We're actively looking for ways to make these as efficient as possible to speed up our optimization process. Again, get us to predicting those treatments that can keep our T cells in as healthy a state as they can be. So with that, I'd like to thank my group. Tolu, Jordana, and my master's student City have done an incredible job setting up their projects over the past year. I'd also like to acknowledge my group at NIST, where the initial project I presented today was performed. And finally, my sources of funding. Thank you all. I'm hoping to continue some conversations. Please reach out.
Yeah, we're running a little late, so is there a if there is one question from the audience, we can take that. If you're online, you can unmute. Sure.
Yeah, as you said, the solving the PDE is complicated. I was just wondering, are you solving it with any standard toolbox or any domain-specific solver? And how does, for example, the videos you have shown, you have an initialization. So how does that initialization affect the conclusion you might reach?
Yeah, so the sensitivity to initialization is definitely something that we're actively working on. We have noticed a lot of sensitivity, as I may have sort of mentioned, like a sort of spatial dependence or a region dependence. Depending on, I'll give just one quick example, like the timing. So for example, if we let the T cells infiltrate for quite a bit and then we start diffusing our, I'll say like first dose of drug a lot later, the T cells effectively outrun the drug. So it doesn't matter what properties the drug has, it's just not going to be effective. So I guess the number and the positioning of the T cells, especially relative to the therapy, does seem to be dictating a lot of what would be considered the most optimal drug as we're defining it. In terms of how we've set up our system, we are currently using a mix of MATLAB and Python. We are using standard toolboxes provided in MATLAB and Python. And then we're running it through CCR resources. Currently, our tumors are on the order of 10 to the fourth cells, I believe. So just a lot of operations that are happening at each time step. And then trying to run this for a simulated time of, I guess the equivalent, like the time step equivalent of 6 hours. So it's just a lot of operations.
Thank you.
Yes, thank you guys. Thank you.
So thanks, and we'll go on to the next talk. Professor Cindy Lee from the Electrical Engineering Department.
Okay. Hi, everyone. I'm Shimiao and from Department of Electrical Engineering. I joined UB last year and such a pleasure to be here. So today I'm going to give a quick overview of the core research that is being done in my research group. It's called Sparse Act. So basically, it's a toolbox that can enable fast and targeted decision support. So although my main application is on the electrical power grid, but I believe many of the underlying ideas, such as sparse explanation and sparse recommendations, would apply broadly to large network systems. So let me start from a core motivation that being simple is the art of engineering. So usually for complicated engineering systems, we care more about the dominant factors instead of any tiny detail. So the same for the electrical power grid. When a failure happens, we might ask who is responsible for the failure. So usually the key responsible components are very sparse. So two real events can illustrate this. So in 2019, there was a serious blackout in the UK, so affecting more than 1 million people. But the root cause was due to a lightning strike, causing disconnection of 2 generators. And later last year, there was also a power outage in the UK Heathrow Airport, shutting down the airport for the whole day, affecting more than 1,000 flights. But that was originally due to a fire that is in the nearby substation, and it was affecting one transformer device. So as you could see, although the impact could be huge, the consequence could be widespread, but usually the root cause or the dominant failure source are usually very sparse. So before these failures actually happen, imagine if we can proactively study them and identify some dominant system vulnerabilities, then we can take corrective actions accordingly. So then similarly, when we take actions, sparse actions are usually also preferable to improve the system. For example, this is the 2024 regional transmission expansion planning proposed by the Texas grid operator. So as you see, the lines marked in green here are the lines that are being proposed to be installed in the system to improve the service. So you can see only a few lines. This makes sense because installing new infrastructure is very expensive. And in general, we are doing real-world decision-making, like installing new power plants, new lines, new battery systems, and also new, for example, reactive power compensators. We're always interested in knowing what are the optimal locations and what are the optimal sizing. And we're always interested in making our locations as sparse as possible. So technically, to make such failure diagnoses and troubleshooting, simulation method is the key. It's the foundation tool. So before we tuck into more details, let's look at how the power system and its potential failures can be modeled. So depending on the condition of the system, let's categorize the system into 3 different conditions. So one is the normal condition, which means the system satisfies equality constraints, which represents balance. And the balance means the supply must meet the demand everywhere. And we also have inequality constraints that represent some operational bounds. For example, the voltage, the frequency, and some line flows must be bounded within an acceptable range. In a normal condition, all of them are satisfied. But then in a severe condition, we have that balance is still satisfied. But there are some operational bounds violated. For example, some voltage might be extremely low or some lines are overloaded. And then most seriously, the blackout case, which means mathematical, the system becomes infeasible. We don't have enough supply to meet the balance. And also we're violating the bounds. So unfortunately, standard simulators will diverge when the system is under a blackout scenario because there's no feasible solution to the balance equations we're solving. So then, obviously, we need a simulator to be effective in all these 3 regions. And that's my research goal. That is, could we leverage some sparse optimization such that we can pinpoint some key vulnerabilities behind those failures, such that we can suggest some fast-acting, targeted corrective actions. So let me start from the most catastrophic condition, which is blackout. So imagine we're planning for extreme heat event during the summer, which drives our electricity demand to be very high. And if we do not have enough supply, power outage occurs. And in this condition, an immediate idea is let's build more power plant to supply the electricity. But theoretically, there are infinite ways of building power plant. So suppose I'm a generator, and you need power. So one option is I build a bigger generator at my location and deliver power to you. Or you can build a smaller power plant at your own location to meet your own demand. Or each of us can build a small power plant. So there are infinite possible combinations. But by doing sparse optimization, we're able to tell the minimum set of locations. So here in this example, we're saying, hey, this node, this red node is one location where you can add that amount of compensations to meet balance hold again. And that is a sparse diagnosis. Say this location can be considered as a dominant failure source for this blackout. And also, it represents a sparse recommendation that if I want to fix the problem, I need to build at least one power plant at this particular location at this particular amount. And the method behind this is also straightforward. So let's consider as a network system. We can try to introduce new compensation variables at some controllable locations. And then we integrate those new variables into the network constraints. And then an optimization problem try to minimize those total amount of compensations, while meanwhile makes things sparse by adding a regularization term. And once we solve this, we get sparse compensation vectors. And instead of just solving one particular extreme events, we can also extend this to a sequence of events. So imagine we're doing planning for 10 years. So every year, the electricity demand increase a little bit. So in this case, we're doing sparse optimization to return a persistent trajectory of sequence of solutions. So being persistent here means, for example, here in these three figures, so we are installing 2 power plants. And when demand continue to grow, these 2 power plants increase its capacity. And then we demand increase to a point that 2 power plants are not enough. Then we consider adding new additional power plant so that it's in total 3 power plant. So kind of as a smooth evolution of your decisions. So things can be more clearly illustrated from this numerical plot, where here on the left, the x-axis representing the growing load level, where the y-axis representing the locations where you want to make compensations. So if we define the set of locations at each step, right, as ST. So persistency here is defined as a nested sequence of subset, which intuitively means the set of locations you identified in previous steps will continue to be useful when the condition becomes worse, instead of just abandon it. So by comparison on the right, if we do not consider persistency and simply run each scenario separately, then the result could be inconsistent. So at some point you install a power plant, but at the next step you abandon it. So this is unrealistic planning strategies. And further, so let's move forward to integrate more inequality constraints into the framework. For example, some operational bounds. So let's start from keeping the frequency within an acceptable range. So we all know, for example, in the United States, the power grid has a nominal frequency of 60 hertz. So we must maintain this frequency in order to be reliable. So however, when a disturbance happens at some time, so we look at the transient horizon, the frequency will temporarily drop. And then the droop control within each generator start to react. So it compensates for more real power. So as is shown on the right. So as your frequency drops, moving to the left, you produce more power, right, to compensate for the mismatch. And by doing this, the frequency will go back a little bit until reaching a steady state. But there's still a deviation, delta F. And that steady state deviation can give us some insights into the system stability. So if that deviation is very large. That means the system cannot be restabilized back to a very good state. And from a decision-making perspective, if we can take action to make this deviation small, then that will help stabilize the system. So that's our high-level idea. Let's integrate this group control modeling in our network constraints and also enforce some bounds on the frequency deviation. And here's a toy example. So on the left, on this small system, when a generator outage happens, if we do nothing, the frequency will drop by more than 0.5 hertz, which makes the system unstable. So then we bring a frequency bound into the system, limiting that the frequency deviation cannot exceed 0.3 hertz. Then after doing that, a sparse optimization will recognize that we can make compensation at node 13 in order to make the frequency deviation bounded to our acceptable range. So that's the high-level idea here is a very sparse localized compensation can stabilize the entire system. And this also applies to very large-scale systems where we can simulate a lot of scenarios. So you can see this particular scenario is having frequency dropping below our threshold. So on the right, we do a sparse optimization and set our frequency bound. Then we recognize 4 compensations made on this very large system, and that can bring the frequency back within the threshold. So again, the compensation is sparse and interpretable. So then let's move one further step. Say, could we incorporate more bounds? For example, the voltage bound and the line flow limits. So line flow limits here means the maximum amount of power that can be delivered in a transmission line has a maximum bound. And here's also a comparison example where on this large system, if we do nothing, there are some nodes having under voltages. So the voltages are falling below the minimum acceptable level. And also there are some lines having overloading. But on the right, if we can recognize some compensations at some localized locations, we can mitigate all of these problems. And further, to help real-world planning, so could we put more requirements on the type of compensations? So suppose we're going to make compensation with some new devices. It could be a power plant, which supplies both real power and reactive power. Or it could be a reactive power compensator that supports only reactive power. So in reality, if you look at your electric devices, like your laptop and your computers, so there are several important values. For example, one is the nominal voltage. So it needs to operate under some particular voltage, for example, 110 volts. And also the power, where the power needed usually by the device is the real power, which we need to consume. But in the electricity field, there's also another power called reactive power. So that reactive power we do not consume reactive power, but reactive power is used to support the voltage such that the voltage is what we need. So now that we have voltage issues, let's restrict all the compensations to be only reactive power. And by comparison, you can see that we recognize 30 locations on this very big network to install new reactive power compensators. And that can mitigate all the voltage violation issues. So for all these results above, so a key thing is sparsity. The key thing is to get sparse solution. So then the question is, how could we efficiently encourage sparsity and get our solutions we need? So ideally, we want the solution to be as sparse as possible because we want the minimum set of locations. But this is not easy because one challenge is ill conditioning. So using some traditional method like lasso to enforce sparsity, it's usually need a very high parameter to penalize the non-sparsity of the solution. So, and this leads to ill conditioning. One of our prior works looks into this from the optimization landscape. So from an optimization view, so this one term which enforces sparsity is non-differential. So let's first convert it to a differential optimization problem by introducing some additional variables t, and that transforms into some inequality constraints. And that inequality constraints, if we solve with the interior point method, will correspond to some perturbed KKT conditions. And this is a nonlinear perturbed KKT condition curve. So if the C value is very high, your coefficient is very high, then you're making your optimization to converge around a very difficult optimization region, which is the steep region on this complementary slackness curve. And thereby, when you linearize the system and iteratively solve it, it leads to some bad conditioning on the Jacobian matrix, which cause your convergence to be very slow or imprecise. So to address this, we are trying to build a new method. So the key insight is that we make the coefficient not a scalar, but location specific. So for each location, it has its own coefficient. So we do not rely on making the solution sparse by making the coefficient very high. Instead, we try to encourage sparse solution by making those coefficients very different across the different locations. So unevenness promotes sparsity. Specifically, so originally this is a zip file. So we start from solving a dense optimization problem, which leads to many compensations. And then we gradually shrink the number of locations we return until reaching only one optimal point. So, and at each sub-problem, we try to toggle the location-wise coefficients between 0.1 and 10. So according to my current compensation values. So if the existing result tells me that the compensation is very high at this location, then I make the threshold low, make this coefficient low. Otherwise, I make this coefficient high. So in this case, I gradually promote the compensations to flow in those cheap locations and until making those cheap locations very sparse. And furthermore, we also leverage some artificial intelligence to further speed up the optimization problems as previously proposed. So basically, we use some machine learning to predict the solution that might come from those simulations. So those predictions are then used as initial guess to initialize your optimization engine. And here's a comparison with different initialization method, and shows that using machine learning as a warm starter can significantly reduce the amount of time you need to simulate your result. So even on this very large 2000 bus power system, it can achieve more than 3 times faster than traditional initializations. And here are some key takeaways today. So sparse optimizations can help us diagnose key system vulnerabilities and also suggest some targeted corrective actions to mitigate failures. And further, with AI-based decision support, we can further enable faster and more scalable analysis. So a lot of exciting things are going on in the field of electrical power grid, and I'm happy to take any question. Thank you.
Any questions?
A really interesting talk. I was curious if you could say a little bit more about your AI warm starters. Was it like a neural net, or how exactly did you implement that?
Yeah, it is a neural network, but it's more like a graphical model, since power system can have different network structures. So how could we make the model generalized to different network structures? We propose something called a probabilistic graphical model, where, for example, at each different node, we have a node neural network. At each different line, we have a line different network. And then those different locational neural networks are put together to form the entire global solution by a probabilistic graphical model. Yeah, thank you.
Yeah, no, super interesting. And actually, one other quick question. The graphs that you showed, were they, did you say that they were based on like a real location, like a power grid in a real location?
Do I rely on what?
Were your grids based on like the power grid in like any particular city or like metro area?
Yeah. So all these systems we are showing, it represents some synthetic realistic grids that comes from public data. Yeah. So the lines represents a real world transmission lines. The node represents a real world substation, which either generates power or consumes power or just transmits power.
really interesting work. Thank you.
Are there any questions online?
Oh, there are online attendants.
Yeah, there are people there. Yeah, I mean, both were really interesting talks. So you can unmute and ask your question. There was a question. Maybe not. All right. So yeah, thank you again. And yeah, both were very interesting talks. One on the power grid, the other one attacking cancer cells. So yeah, here's a small token of our. Yeah, thanks everyone for coming. And yeah, these talks will be online, the videos, so you can share it with other collaborators as well, other potential collaborators. So